morning. First of all, I would like to thank the organizers here for giving me the opportunity to speak today. I would also like to thank all of y'all as an audience for coming out here today, spending your Saturday here, and being a very mentally involved audience, as I've mostly observed. So that's going to make my job a little easier. Thank you for that. So I am here to talk to you today about why the sky is blue. Ever since elementary school art classes, we know to paint the sky blue in our stick figure images. But since then, have we really thought about why it is blue? So I'm here today to try to qualm that curiosity and maybe debunk some misconceptions. So a common misconception for why the sky is blue is that it is reflecting the sun, the seas, and the oceans. So let's talk about what is actually happening. First of all, what is the sky? So when we think of the word sky, we probably think of the first image. But to talk about what is really up there, above the Earth's surface begins the Earth's atmosphere, which is composed of a mixture of several gases, mostly nitrogen and oxygen. While this is well known, that there are gas particles in the atmosphere, we don't always think about what they do there and the role they may play. So a lot of the times, even right now, you have gas particles around you, but we often neglect thinking about them because we don't see them. So what happens with the gas particles in the sky is that when sunlight travels through the atmosphere, the light is scattered by the gas particles. So before we talk about the scattering and the color and why the sky is blue, let's have a little refresher on light. So this is everything we have probably encountered at middle school science class, but let's just do a little refresher. So light, when we see sunlight, we don't associate one color to it. It is composed of all the colors in the visible spectrum, which is why when you pass light through a prism, it can refract to show the different colors in the rainbow. The different colors in the visible light spectrum are attributed to the different wavelengths of the light that can be seen by the human eye. So what makes the difference in these different colors of visible light is the wavelength. And the wavelength is defined as the distance between the two high points in a wave. So if we look at the red wave, we have a longer wavelength. The distance between any two high points is longer than a blue wavelength, blue light, let's say. So the point that I want to point out here is blue and even more so violet have the shortest wavelengths and have the highest energies in terms of visible light. So the concept that helps explain, or the phenomenon that helps explain the way that the sky appears to be blue is called Rayleigh scattering. The first time that I encountered this was during my time earning a bachelor's degree. So I don't blame y'all if y'all did not want to earn a bachelor's degree. So let's talk about it now. Rayleigh scattering is named after Lord Rayleigh, the British scientist who discovered this phenomenon in 1871. It is described as a scattering of light by molecules that are smaller than the wavelength of visible light. So what is different about Rayleigh scattering as opposed to other ways that light is refracted, like in a prism, or reflected all around us, is that the medium that the light touches, which is the gas molecules in the air, is smaller than the wavelength of the light. So in the last slide, I talked to you about the wavelength, the distance between the two high points. The gas molecules, nitrogen and oxygen, are smaller than that wavelength. So that is what makes this kind of phenomenon different than other ways light travel through mediums like prism. So when light is scattered by gas molecules, there's a little typo on the screen, when sunlight is scattered by the gas molecules, the shorter high energy violet and blue light gets scattered first and the most. So it is thought that violet light scatters too fast for our eyes, and our eyes are not as sensitive to seeing the violet light. So most of the time we see the scattering blue light. So this is why we see the sky to appear blue. So now you may ask, well, the sky isn't always blue. One of the biggest examples is sunsets and sunrises. Why is the sky different during sunsets and sunrises? This is also explained by Rayleigh scattering. The difference is that the sunlight approaches at a different angle. So most of the time during the day, when the sky is blue, the sun is above us. So kind of in this area. But as the observer, if I'm the observer, but during sunsets and sunrises, the sun is to our side, so 90 degree or 180 degree from the observer. So what happens at this new angle, if you look at the first image at the top, when the sunlight comes from the side of the observer as opposed to above the observer, the light travels through the atmosphere for a longer period of time. And when that happens, as I said earlier, the first colors to scatter are blue light. So in the beginning of the travel through the atmosphere, all the blue and violet lights get scattered. So by the time the light continues to travel through the observer and meets the observer who is witnessing a sunrise or a sunset, the colors that are left are orange, yellows, and reds. So the higher wavelength colors. So this is why at the new angle, when the light travels through that larger distance, we don't see blue light anymore. We see the larger wavelength red, yellow, oranges. To conclude my presentation, we often encounter this, or many of us probably encounter this statement. It is said that he created the skies and heaven on the second day. After this presentation, I encourage you to ask them, well, when did he create the gas molecules that are scattering the light you're seeing? Thank you.